So today the name of the game will be control theory, and we are at the interface between theory and experiment. So there's a bunch of questions a quantum engineer would naturally ask, and the answer to these questions sometimes really brings you in, if you want to answer them rigorously, fairly deep into mathematics. And with this being an institute of mathematics and physics, today I also enjoy the luxury of, say, sharing some of the mathematical details, including some bits and pieces where we are still working on, and I hope that might trigger discussion. So you may ask to which extent a certain quantum system, you know the equations of motion of, and you know the initial condition of, can be controlled. That's a natural a question to ask in closed systems. In open systems are never ever really controllable because you cannot sign reverse all the directions in a truly open system. So their accessibility simply is the generalizing notion of controllability, which simply means during the time evolution of your state, the state visits all the dimensions of the state space and has non-empty interior in the state space. So that's accessibility. And one of the important questions, probably also for the motto of this workshop here, is to which extent you can simulate quantum systems. Say, quantum system A simulates quantum system B, and can one give some rigorous conditions when this is possible or not? And in view of sensing, you would wish to ask to which extent can these states be observed or sensed, or to which extent a certain process can be tomographied. And all of these questions are, so to say, the natural questions of engineering. And in classical physics, there are many methods of handling these types of questions. And the name of the game of today is to see to which extent one can lift these notions, which are very natural, into a mathematical frame that allows rigorous answers once one is in the quantum realm. So that's, so to say, the menu. And the nice thing here simply is that to a very large extent, all these features are already encoded in the Hamiltonians of your closed system or in the Lindbladians of your open system, in particular if it's Markovian. So there is no approximation when you go to linearization. You simply start to really get the fingerprint of the generators, and the fingerprint of the generators translates into the fingerprint of the dynamic group in closed systems, or semi-group, as it were, in open systems. And by fingerprint, I mean a fingerprint in terms of symmetries. So that's the overarching frame. Needless to say that all this can be put, this overarching frame comes mathematically in the disguise of Lie groups or Lie semi-groups. And that's exactly the frame in which I'm going to put these questions and try to answer them. So, quantum systems theory. So it's simply an input-output type of black box relation. You have an initial state, you have final states, but of course you have a control unit, and that's usually something classical, which then interferes with the quantum system itself. And in a semi-classical picture, for instance, the degrees of freedom by which you manipulate your system simply turn up in the disguise of control Hamiltonians, as I will show in a second. And usually these controls, they're just being administered piecewise constant. So simply think that you have a digital waveform generator, arbitrary one, and that's the name of the game. And of course, as I said, we borrow a lot from classical systems theory, and one of the key players here is Kalman, the late Rudolf Kalman, who worked on linear systems and answered many of those types of questions, and without the Kalman filter, the Apollo program wouldn't have been that successful that fast. And then there are bilinear systems. I'll tell you the differences in a second, where the key players are Djurcevic, Sussman with his parrots, and Roger Broquette. And bilinear systems are simply characterized by the following pattern. That's here. Let's simply start with the second line. The lowercase always represents a vector, whereas the operator lift is then written in upper cases. So here you would have a state vector, the time dependence of which depends on a non-switchable term, that's the so-called drift term, and a number of time-dependent, piecewise constant control amplitudes in red that govern the control operators B. And in this frame, it's essential here to see that the drift term cannot be switched off, whereas the control terms, they can be switched on, off, and manipulated in arbitrary fashion. This might sound a little abstract to you, but you will immediately see that instead of x, if you simply put a state vector, and here the drift Hamiltonian, and here the control Hamiltonians, this is nothing else but just the controlled Schrödinger equation. And therefore, this is nothing else but generalizing it, lifting it to operators. For instance, if you want to have the equation of motion for synthesizing unitary gates, capital X then simply is a member of the unitary group, and that's the equation of motion. And you see, since the list here is very long and reaches from pure states to mixed states to unitary conjugation to density operators to quantum maps, you see it's one and the same pattern reigning a plethora of applications in quantum dynamics. Okay, so let's have a look in slightly more detail. And let me simply give you an upshot of the keywords which will be reigning the rest of my talk. So here we have our bilinear control system. And the nice thing simply is that, as I told you, the time dependence is totally governed by the generators. And this simply comes here by these drift and control Hamiltonians, as we saw in the last table, and the Lie brackets. And the system algebra here simply is the linear span over all nested commutators until nothing new, linearly independent arises. That's the system algebra K. And if the system algebra K coincides with the unitary algebra of all skew Hermitians, then you know that your system is universal, and it would be your experimental system having such a system algebra would be a candidate of a universal quantum computer or quantum simulator. If K, as it sometimes occurs, is a proper sub-algebra of the unitaries, then you cannot perform every task, and it's not a universal machine. But nevertheless, there's a rigorous answer to what is called the reachable set. And the reachable set here, you see K is compact, is simply the group orbit of the initial state. And that's the set of all reachable states. So the reachability problem here in closed bilinear quantum control systems is very easy to answer just by group orbits. And then, as I told you, symmetries play a key role. And for the symmetries, we usually don't take the Hamiltonians in their bare form, but simply go to their adjoint representation, which is simply the representation as commutator superoperators, which you may choose, and that encodes the full fingerprint. The naked Hamiltonians themselves don't, but their adjoint representation does. And then the symmetries simply are those elements which are in the commutant of the adjoint representation of A and all the B's simultaneously. So then, in this case, the system simply would have a joint symmetry. And as you know, whatever commutes with the Hamiltonians is a constant of the motion. And therefore, it's immediately obvious if you have a non-trivial commutator, your system cannot be universal. And the nice thing here is that the symmetries are usually easier to come by than calculating the Lie closure. The Lie closure is time-consuming, it's numerically touchy at some points, whereas the symmetries are usually much easier to come by. And here is a theorem which we worked on together with Robert, who was a key player in that, and then Zoltan joined. So in the first part, let me also simply introduce a little bit of the key players and their contributions here. And as I said, if we study the symmetries, the commutant of the adjoint representation, then obviously the big identity is a trivial member of the commutant, so I won't talk about that any longer. And it turns out that the projector on the vectorized identity also is. That's, so to say, an indicator for unitality. It simply means that the identity is a fixed point. And you see, if we have irreducible, simple, proper or improper subalgebras of the unitaries, then there are certain types of branches, orthodox branches, an orthogonal one, a unitary symplectic one, and from time to time also another unitary one, which is not of this blue or red nature. And that's what one has to discern. So the question is, under which conditions are we top of the branch? That's full controllability. If we are somewhere within the branches, then we don't have full control. And here these guys, and we will dwell on them a little longer, they are usually coming with a Cartan decomposition. And this type of Cartan decomposition simply means one has an intertwiner. So for instance, if the Hamiltonians are skew-symmetric here, then simply S would be the identity. And this simply means that the Hamiltonian here is skew-symmetric. Or otherwise, it's unitarily conjugate to something skew-symmetric, and that's our general notion of being unitarily equivalent to the orthogonal group. So as soon as we have such an intertwiner, the intertwiner itself adds a further symmetry. And in this type of adjoint representation, these types of intertwiners simply come in and utter themselves as a symmetry, and therefore here in the branching diagram, by additional symmetries, one can simply rule out that one has full controllability, because then one is on some of these branches. So that's the idea. Currently, we are also looking into slightly more generalized pictures here. So the adjoint representation is just one choice of a representation which simply carries all the information. And currently, we are having a look here at this version, where we simply have a Lie automorphism just working here on the first tensor component of this type of representation. And then when one has such Lie automorphism, then the different types of representations just interrelated by these types of Lie automorphisms also share the same number of symmetries, and the symmetries can be simply calculated back from one representation into the other one, which sometimes is very helpful, because at times it's easier to pinpoint the symmetries of the adjoint representation, whereas in other cases it's easier here to, instead of theta having a non-trivial role, simply taking theta as an identity, and then one has what we call the symmetric Kronecker sum or tensor square type of representation, and sometimes it's easier to use that. And here the same thing happens, so the intertwiner here immediately translates into this symmetry element, and that's something which is easy to see in this type of representation. But you see, I'm simply adding these bits and pieces in view of further discussion with my friends and colleagues, and I simply don't want you to bother too much, but suffice this here simply to tell you that it's easy via these partial Lie automorphisms on one tensor component to calculate symmetries or shift symmetries from one representation to the other. Okay, let's get back to the main track. One very practical implication of all this is if you have two bilinear control systems, sigma A and sigma B, with system algebras Ka and Kb, it's obvious that system A can simulate the dynamics of system B if and only if the system algebra A includes the system algebra B as a proper or improper subalgebra. If not, the simulated system would have more degrees of freedom in its dynamics than the parent system A can simulate. So this is a no-brainer algebraically, but probably you have never thought about this, and it's an easy check to see whether certain quantum simulation tasks are well posed or ill posed. And one can go a step further, which again we did with Zoltan and Robert, and simply say that here the subalgebra B equals a subalgebra A of the unitaries if and only if they share the same symmetries on the pertinent state space and the ranks of their central projections also coincide. So that's, so to say, something like a group or an algebra inclusion relation, which also is simply reigned by the symmetries. To put some flesh on it, let's simply take spin chains. And we simply have a spin chain here where we can only control the front end. So this here stands for a qubit. So that is SU2 controllable. And we simply have Heisenberg XX type of couplings to its neighbor. And all the nearest neighbors are also Heisenberg XX coupled. Let's see what such a system here has as dynamic system algebra. And here it turns out that the system algebra is SO2n plus 1. And you also see that with the number of qubits and levels here, the number of degrees of freedom of the system, so to say, the size of the algebra grows linearly. So this is something like, so to say, a classical type of quantum simulator, or a quantum simulator with classical scaling behavior to be more precise. And if we add further controls on the end, then we simply go into slightly higher dimensions and a different type of character of the orthogonals. We go from the orthogonal to the unitary character here of the orthogonal group, which is of no particular interest for the rest of this talk. But you see what happens if we shift the control here from the front end to the second one. And that's really very interesting because you see then the bets are loose, and just by reflection going back and forth, the system algebra really raises, and it's 2 to the power of n. So this is a quantum simulator with a quantum speedup. This is really a full-fledged quantum simulator whose size grows exponentially with the numbers of qubits. And as Robert found out, there's even something more, which is very interesting. So if the chain length here, mod 4, is 0 or 1, then we are in the orthogonal realm. If it's 2 or 3, then we are in the unitary symplectic realm. So the quadratic terms, so to say, here in this case behave as if they were fermionic, and here they behave as if they were hardcore bosonic, so bosonic with fixed numbers of levels. And you see, without the system algebra and its nature, it would be very, very difficult to characterize the dynamic behavior of such spin chains. And if you have two neighboring controllable ones, then you have the full-fledged algebra. So you see here all the different types, the full-fledged one, the orthogonal one of unitary type, and the orthogonal and the unitary symplectic ones, they occur. So the abstract branching diagrams themselves here, they really have some concrete experimental incarnation, and you see it's easy to characterize these systems just in terms of these algebras. With Zoltan, we went a step further and had a look into fermionic modes, where we just have a parity, and the parity operator simply divides the system algebra into blocks, and further symmetries then come with further restrictions, and you really can play the game here and study additional symmetries and their system algebras. I'm not going to dwell on this, but you see this is something where if you are interested in that, then Zoltan and Robert, they are the key players in this, and they will be able to answer further questions. But you see, let me simply come to a more recent topic. And you see, if we have these, if we have the quantum system theory and observe it, there is quite a bit which one can learn already from linear systems theory, because it's an observed bilinear system carries the dynamics of a bilinear system and the observability properties in a way of the linear system. And to be more precise, let's simply have a look at a linear control system for the moment. So that's what many systems theorists simply do their entire life. They dwell on dynamic equations which are of this kind. So that's the drift part here, which is linear, and then one has a control operator plus additional vectors which can be fed into such a linear system, which in quantum mechanics we cannot do. But nevertheless, here the algebraic properties of such a linear system are very interesting, and it's simply such that you have a controllability matrix which simply takes the matrix B and then all the powers of A pre-multiplied with B, and if this gives us a full rank matrix algebra, then the controllability matrix is of full rank, and the linear system is controllable. In linear systems, there's a duality between controllability and observability, and that's expressed here by this linear observation part. And there one has an observability matrix, and there you simply right multiply the observable operator with all the powers of n, and you also have to get the full rank. And therefore, here we really see this very nice duality principle of linear systems. A linear system is fully controllable if and only if the dual system is fully observable, and vice versa. And in particular here for the observability part, that's something which we would wish to memorize for the further discussion also of bilinear systems. And bilinear systems follow this type of equation of motion, but very early on already one of the key players, Isidori, simply had a look, so what happens if we just have a constant control which does not change in time? In the previous tables you saw that u was u of t, and I told you it was piecewise constant. Now let's simply specialize the discussion to a constant u, which simply puts on a certain drive. So one can simply sum these two, and then, of course, one has this type of linear system. And then one can ask oneself, so we simply project here x of t on the observable operator, and then we simply take the observability condition, and that gives us the observability matrix. And that's exactly what one can learn for bilinear systems from the linearization to linear systems. So this is the observability matrix. Remember that for a couple of slides further on. So now let's get back to our original setting of bilinear control system where we have piecewise constant controls, but we simply take this linear type observation, where C is an observable and rho of t, of course, is the density operator at the pertinent time. Remember here that H0 and Hj, with J being all the control Hamiltonians, simply determine the system algebra, which is in closed systems a sub algebra of the unitaries, as we had it before, and the reachable set is simply given by the K orbit. Now, one of the early players in quantum control theory was Domenico DAngelo, who also wrote a book in 2008, and there he defined that such a system here is observable by way of the observable C, which here is simply taken to be a self-adjoint or in finite dimensions Hermitian matrix. If for any pair of states, we are only taking the traceless part here, the equality here for all times of the expectation value between the traceless parts occurs if and only if the traceless parts of the two pairs of matrices are the same. So if the expectation values are the same for all the time, then the traceless part of the density operators are also the same. And if these two equations are equivalent, then we say the system is observable. So any difference between states can be observed by different expectation values at some time. Very natural definition. And what he did not discuss, but what reflects nicely what we had with these linear systems is that not only do we have a reachable set, but you see by this trivial invariance of the trace under cyclic permutations, we immediately get something like an observable set. So that's simply, so to say, the dual group orbit of the reachable set. And then it's obvious that one can take a tangent space. And that's, so to say, simply simple commutators taken here from the system algebra impinging on the I times the traceless part of the observable. So that's the tangent space. And now comes the observability space, and here I'm taking the definition of Grasselli and Isidori, which we had above. And there we simply have members here in the observability space, which are simple commutators of elements in the system algebra. The difference between the system algebra or the Lie closure over the Hamiltonians plus the observable would simply be that one could also insert the observable here on the left-hand side. So then we would have a Lie closure and we would have a Lie algebra. Here we just have, so to say, tangent spaces of all order. And therefore, the observability space naturally is a linear space, and it need not be a Lie algebra. I'm going to tell you some of its structural issues in a second. Let me simply come back to D'Alessandro, and he simply observed that such a system is observable by such an observable C, if and only if the observability space is the entire Lie algebra, and it simply exploits all I times the Hermitian operators. And if you can simply exploit all the Hermitians, then you know that your space is informationally complete. So this is a very natural theory. Okay? And he also observed that it's sufficient. There's a sufficient condition for observability, which simply means that the system is fully controllable. This condition is sufficient, but it is not necessary. And that's the difference between the classical and the quantum realm. In the classical linear systems theory, there's a duality between controllability and observability. And here, there is no such relation, and controllability is stronger than observability. The simplest example is the following. Simply take a two-level spin system. The controls are just y pulses. The observable here is the sum of sigma z and sigma y. And the observability space, obviously, is the entire Lie algebra SU2, because you simply commute y with z to give x, y with y gives 0. And then you take further, and then you take a second time the same commutator, and then you get back sigma z. And therefore, you have sigma x, sigma z, and sigma y in your observability space, which simply means the system is fully observable, although obviously by a single control, it's not controllable. Okay? So that's the simplest example, and it's already mentioned by D'Alessandro. Okay, so that's our observability space, the system algebra. And now let's simply have a look into the structure of this observability space. The observability space is a Lie algebra. Whenever we have the following situation, we have a semi-simple real Lie algebra as a as system algebra, which sits within the unitaries and is just the k subpart of the unitaries in our Lie picture. So could be the orthogonals or the unitary symplectic ones, for instance. And if I times the observable comes from the same algebra, the tangent space simply takes the form of Lie algebra, because it's obviously Lie closed. And that's simply due to the fact that whenever you have an element in K and you commute it with another element in K, here our system algebra, you do not leave K. So that's what explains line 1. In contrast, if your observable is in the P part, then commuting some element in P with K never leaves P. That's the Cartan relation. So here we are in a symmetric space. And only if the observable has two non-zero legs, one in the K part and one in the P part, then we leave these special structures and we are really in a linear space. Okay? And this linear space could, in principle, be the entire unitary algebra again, at most, but it need not be. So let's have a slightly closer look. And that's very easy by way of the following example. Simply take a two-qubit system where you have full control over the first qubit by x and y pulses, full control over the second qubit by x and y pulses, and your observable is ZZ. Then it's easy to see that the observability space is just the entire symmetric space, because we are exactly in this situation. Okay? And this symmetric space, that's the observability space, and you don't leave it by way of the Cartan relations. Now, if we add further components here to our observable, namely a Z component from the first qubit and a Z component of the second qubit, then the following happens. The commutation here of the ZZ part reproduces the entire symmetric space again, as we had it in the previous example. But here, the X and Y pulses on the first Z operator, they give you the full SU2 on the first, and the second ones on the second. And therefore, you have the entire SO4 algebra, which is a semi-simple one, and decomposes into an SU2 on the first qubit and an SU2 on the second. And the blue part here gives you the full algebra K sigma, and the red part here gives you the full symmetric space, and both of them add together to really give you the full unitary algebra. So in this case here, your observability space is complete, and this system here is observable. And in the following 2 or 3 slides, I'm just formalizing the observations which we did here, because you see here we have a semi-simple case, and if our observability space is such that it encompasses the entire symmetric space and all the K parts in every of the semi-simple components, then we are done, and the system is observable. So that's the slide which we had before. And now let's simply go from such a system which may be of arbitrary nature to one where we know that we have a simple, irreducible subalgebra, and then some interesting features happen. So if we have such a simple subalgebra, and it's a Cartan subalgebra of the full unitaries, then we have this intertwiner, which we were making use of in the controllability discussion. And if the vectorized form of this intertwiner, indicative, for instance, of the orthogonal system algebra, is also in the kernel of this symmetric square of the observable, then we are in the K part, because that's exactly the criterion which we were using for the controllability issue. So if this here is in the kernel of this symmetric square, then we are within the K part of such a Cartan subalgebra. And you see here, going from the K part to the P part just means we change sign. And that's simply the intertwiner relation here. And you see, if we test that S is neither fully in the kernel of the observable, in the symmetric square and in the antisymmetric square, then we know that we have 2 legs, one non-trivial P leg and one non-trivial K leg. And in a simple algebra, since there are no further invariant ideals, you are done. And here we finally have equality as we want. And you see, it's more or less the same type of symmetry criterion that we had for the controllability. But here we have additional symmetries to check the symmetric and the antisymmetric square, because controllability is a stronger condition than observability, which simply means that observability may have more symmetries, which have to be checked. And that's exactly what establishes observability here in this case. Yeah. Then one can do this for simple algebras. That's this double check of the previous slide. And the semi-simple case, the semi-simple case then is very easy. You simply do that for every simple component. So now we have symmetry criteria also for observability, in particular when we have Cartan subalgebras. Okay. Let's get one step further and have a look what happens if we want to tomography a system. If we want to tomography a system, we have to be able to prepare of every state for an input and then observe every state at the output. So we have forward state preparation and backward detectability, observability. Now, in closed systems, we have learned that observability is weaker than controllability, and therefore the situation there is very easy. A system is tomographiable by C, if and only if it's fully controllable, because that guarantees that we can get all inputs. And this is already sufficient to be able to detect all outputs, provided C is, the traceless part of C is non-trivial or non-zero. So tomographiability in closed systems is very easy. And it can be discussed with symmetry criteria just as controllability can. Things become more subtle if we are now in open systems. So we have our bilinear control system here, and on top of the Hamiltonian drift term, we now also have a dissipator, and in the Markovian regime, we may assume without loss of generality that gamma is of Lindblad-Kosakowski form. And then, and that's simply a shortcut, such a system here, such a Markovian system is the solution of a Lindblad-Kosakowski equation. By way of Michael Wolff's and Ignacio Sirac's work, we know that it's infinitesimally divisible to be Markovian and a solution of a Lindblad master equation. And in 2008, we also established that this Markovianity nature allows us to represent the solution by a Lie semigroup. I'm not going to dwell on the details of Lie semigroups here. I'm simply raising this as a buzzword. And the generators in a Lie semigroup, they are simply members of the Lie wedge. And the Lie wedge is simply a wedge cut into the big system algebra, which is simply the analog of closed systems to open systems, where you simply take the Lie closure over the entire drift term and all the control terms, and that sits in the n square by n square dimensional matrix algebra over the reals. And this wedge is the fingerprint for such an open Markovian system, the propagators of which simply form a Lie semigroup. The reachable set, then, simply is the Lie semigroup orbit of, say, the vectorized initial state, then. And the Lie semigroup is globally generated by products of exponential maps of members of the wedge. So that's the shortcut. Lie semigroups themselves are an order of magnitude more subtle than Lie groups. So you will be very happy that I cut the discussion at this very point and spare you further details. But let's simply see how now tomographiability will translate into this frame. So obviously, since we cannot prepare every state, because the system is not fully controllable, we can only prepare states, say, up to a certain dissipative loss. It's natural to simply say that an open system is, so to say, weakly tomographiable if at least all the states can be accessed, not really reached, but you can at least access all the dimensions. And on the other hand, the observability space, again, has to be informationally complete. And now the subtleties, some subtleties arise which we are currently working on. The subtleties being the following, that it's easy here to put the first condition into, you simply transcribe it into the definition of accessibility, which simply means that the semigroup orbit here of your initial state has to have a non-empty interior in Liouville space. It has to visit all the dimensions of your Liouville space without a guarantee that you can really get all the states, but at least you see all the dimensions. And now comes something very interesting. Sigma is observable. The open system, Markovian system, is observable by C if the reachable set of the traceless part of C under the dual channel. So that's, so to say, going from this Lindblad representation to its dual representation by exchanging the first V rho V dagger into V dagger rho V to make it unitary. So if the dual channel here comprises all dimensions necessary for the state to be informationally complete. And you see here, you really see the duality. And that's something which we are currently addressing. So let me simply, as I said in the beginning, gloss over chapter 3 very fast. So you see, for tomographiability, it's crucial to analyze accessibility in the first place. And let me simply gloss over some bits and pieces of accessibility in a fast manner, and ultimately simply close with a couple of applications. Okay, again, here we have our bilinear equation of motion. Gamma is of Lindblad-Kosakowski form. We have a system algebra, and then the following is standard. The system is accessible with respect to all these quantum maps if the reachable set of the identity is a subsemigroup, this Lie subsemigroup of the big embedding group of all n squared by n squared matrices, if this reachable set has non-empty interior in this. So it visits all dimensions. And now, there are some specialties when it comes to unitary systems. So this is the general problem here is a very complicated problem. And there are many mathematical details which are far from being solved, and they are not within easy reach. But let me simply tell you one important little bit which is definitely within easy reach, and that is the following, that if we discuss a unitary n-qubit system, so a system where the identity belongs to the fixed points, then it's map accessible if the unitary system algebra is either the full algebra here, or at least it contains its maximal compact subalgebra. That's something which our colleagues in Würzburg established. And this is only a special result, a very nice special result, if we have unitary systems and they are made of n qubits, because dimensionality here is crucial for excluding further algebras to be acting transitively. And now this here is easy to check. And let's simply have a look on how symmetries to such a system algebra would look like in the unitary case and in the non-unitary case. In the unitary case, we have a block structure where here we have one empty column and one empty row. That's the signature of unitality, and therefore all elements in the commutant to such a unitary system are a multiple of the identity for the A part, and independently one scalar degree of freedom here for the lower right corner. So we have a two-dimensional commutant. Okay? By the way, this here will turn out to be just the projector on the identity, which you already know from the controllability part, because the identity is also invariant under unitary conjugation. If the system is non-unitary, then the members in the system algebra have this structure, and we only have an empty line on the bottom, but we have no empty row, which also means that the commutant has to be trivial. It's just multiples of the big identity. And now let's simply have a look into the accessibility criterion here. So such a unitary system algebra in n-qubit systems has to have a commutant of dimension 2, and it has to have a k part, which definitely exceeds just the unitary conjugation part. Because otherwise it would be, so to say, a closed system simply embedded into an open system, and the closed system would simply visit only the isospectral set, because under unitary conjugation you can't change the eigenvalues, and therefore you have to go at least one step beyond, and the K part has to exceed just the closed part. So it truly has to be an open system, and this also is reflected by the case that the maximal compact Sub Algebra is larger than just being the unitary conjugation. Okay, and now by the work of our Würzburg colleagues, we know that we have the full system algebra in these two upper cases. So that was what I showed you on the previous slide. And this exceeding, or the K part being larger than ad SUN, that's the third possibility, which simply has to be ruled out. And if our symmetries are trivial, then our system algebra could be either of the three cases, and we only have to exclude option 3, because option 1 and option 2, they would guarantee accessibility. And this is very easy because as soon, I didn't write it here, but as soon as you have one element in your dissipator which does not commute with the unitary components, then you are done. So this is something which is easy to verify. So we have a symmetry condition in principle for our system algebras. And here's a huge bunch. Let me simply go to this case here. We simply have Lindblad operators, so phase dissipation on the first qubit. On the second, we have full unitary qubit control. On both of the qubits, we have a canonical drift term. The system algebra is the full one. The dimension of the wedge here as a linear space is only a sub part of it, and the number of symmetries are 2. And you see wherever the number of symmetries are 2, we have a unitl system with a full unitl system algebra. So here we really have a nice correspondence, and here is the pathological case. So if we just have a closed system with no dissipators, by way of the controllability criteria, also the dimension of the commutant is 2, and that's exactly the case we have to exclude. Yep, let me just gloss over these bits and pieces pretty fast. So we have a symmetry condition that does it, and now come two and a half theorems which are important for the last 2 minutes or so dedicated to the applications. And that's a scenario we are very interested in. Let me switch gears now. We have an n-qubit system, which is fully unitarily controllable, but for which we can switch off and on the dominant noise component and simply neglect all the other noise. So the dominant noise terms, they are switchable, and all the other ones are negligible. And if the nature of the noise we can switch is amplitude damping, or simply coupling to a temperature 0 bath, as it were, then the reachability set of such a dynamic system comprises all density operators in its closure. So such a system here is Markovian. It's governed by a Lindblad master equation with a switchable noise term, and it's acting transitively on the entire cone of density operators and can simply turn any target state into any initial state into any target state, at least in the closure. So this is quite remarkable in the following sense. Imagine that you have your favorite pair of states, and you have an experiment which is non-Markovian and makes use of memory terms, and it turns row 0 into your favorite row target. This theorem simply tells you that in a Markovian setting of n qubits, there is a Markovian process that takes the same initial state and arrives at the very same final state, at least in the closure. So for state transfer, Markovian and non-Markovian systems are of the same power. Very strong theory. And this also means that by coupling to a temperature 0 bath, you have something like an intrinsic cooler. So for people interested in quantum algorithms and algorithmic depth, if you have such an experimental system where you can switch on and off this amplitude damping noise, you simply can interrupt your calculation. You are not in the need of taking a fresh qubit. You simply cool one of the qubits, and then you go on. So very powerful theory. That's the symmetry characterization of it. And needless to say here, this is a non-unitary system, and therefore it only has a trivial symmetry, really being the identity, and even the projector on the vectorized identity as a fixed point, of course, here vanishes because it's a non-unitary system, and that fixed point is not part of the stable states. And already the dimension of the wedge has the same dimension as the system algebra. So from symmetric points of view, this is a very interesting and powerful system. Bitflip in its state simply allows you a reachable set, which is only limited by the defining property of unitary processes, which simply means that all the states reachable have to be majorized by the initial state. This is the fingerprint of unitary systems. You cannot avoid it, and therefore the reachable set here in this case is the largest possible under unitality conditions. It's also very interesting, and meanwhile Frederick from Ende, my PhD student, has generalized this setting from n qubits to arbitrary level systems. And one can also generalize it to infinite dimensions. That's also done by Frederick. The Hamiltonian here in this case is bounded, and the Lindblad generators are compact, and then one has the same type of reachable set. So it's a very powerful theory. Okay, so that's what I said. So Markovian quantum maps are as powerful as non-Markovian ones in open loop control, but obviously the operator lift of this is not true, because there are definitely Markovian maps which can be represented as Krauss maps, which are not solutions of a Lindblad master equation, so they are not Markovian. So for state transfer, Markovian and non-Markovian are the same up to closure. The operator lift, of course, gives a precise demarcation between the two. Okay, so these types of noise modulations can be transferred here to the Martinez setup of a Gmon, where the amplitude damping noise simply can be implemented by the typical Martinez type tunable coupling, but now we simply take a tunable coupling to an open transmission line. So that's what mimics our temperature zero bath. Of course, here the tasks we can set are arbitrarily complicated. So we simply went from the maximally mixed state, the high temperature state, to a PPT entangled 2-qubit mixed state, which is very difficult to obtain. And by this type of control sequence here, where the brown part is simply switching on and off the bath coupling, allows you to obtain that with error correction threshold precision. And this state here is fairly complicated, and it's even in the interior here of this nice double prism. It can be obtained by such a regime under very, very realistic experimental conditions. Another way, you see, I told you in the first place, the fewer symmetries you have, the more you can control. And that's also something which has a repercussion in a system, and that's the final topic I'm going to dwell on, and I'll be finished in 2 minutes. Which is of interest here in Vienna, because people are working on these optomechanical oscillators. And if you have weak coupling and weak driving there, then one has a certain type of symmetry, which simply means that Gaussian states are being transformed into Gaussian states, which means one has metaplectic covariance. So one has a kind of symplectic structure, which you also have in classical mechanics. And it simply means that states with a certain amount of entanglement can only be transferred into other states with the same amount of entanglement. So you can form equivalence classes by measures of entanglement, and the reachable sets here in such an optomechanical oscillator, they are doomed to remain within the equivalence classes. However, you can break this metaplectic covariance symmetry by coupling the system to a two-level atom, a pseudo-spin, and thereby the reachable set becomes much larger, and ultimately it allows you to arrive at any kind of oscillator state. And in particular, you can also change entanglement measures, and you can go from Gaussian to non-Gaussian states and so forth. And that's illustrated here by the Wigner negativity. So one really can obtain states with significant Wigner negativity. And here, if you have this measure of entanglement, the log negativity, you really see that during the time of the pulse sequence, the entanglement measure changes. So that's a recent application together with Michael Keil, who really was a key player in this project. Okay, probably I've exhausted you a little bit, so time for the upshot. So our Lie approach here to quantum systems theory that you allowed me to sketch really told you that symmetries really decide what one can do in quantum dynamics in terms of control, accessibility, simulability, and tomography. And in particular, we had a look also at Markovian systems and saw the first incarnations also of symmetry properties in these open Markovian systems. And all this, so to say, then simply backs what you do when it comes to giving advice to experimentalists, because there you use algorithms from numerical optimal control, and once you have established that the problem which your colleagues wanted to pose is well posed, and what you want to do is really within the reachable set, then you believe in these numerical optimizations that really pave the way to high precision applications in quantum technologies, including also sensing. And I'm happy here that we have our friends from Ulm here, with whom we also had collaborations when it came to complicated pulse sequences that allowed certain magnetic fields or certain states to be sensed with high precision in nitrogen vacancy centers. Okay, thanks for listening, and I'm happy to answer questions.
So I had a question about the question of reachability and controllability is of course very interesting, but in practical terms sometimes things can take a very long time. So I know there's this notion, for example, of strong controllability, where you can kind of make certain terms arbitrarily strong to speed things up. And if you could comment on that, and in particular also about...
Yep.
Yeah, go ahead.
Yeah, so one of the issues which is obvious is here that we were discussing bilinear systems where the control amplitudes are not limited. And so in principle, they could go arbitrarily high. And then, of course, you might run into ill-posed problems, in particular if you are asking yourself what is the time optimal control on a single qubit to go from the North Pole to the South Pole. And of course, you simply would hit your spin with a delta pulse of arbitrary strength and then do it in no time. However, as soon as you have a coupling to other spins, then usually the coupling really is very weak, orders of magnitude weaker than the pulse interaction which you can administer. And therefore, in a way, the time is determined by the evolutions under the coupling, and you can't gain by making the local controls faster, which simply says that as soon as you have weak coupling situations, the system is, so to say, self-regularizing. And therefore, these type of delta pulses don't pay, and they also don't show up in the numerical simulations. You can put a caveat and simply cut it, and usually this comes without any effect. Where we did limit the control strength, however, was when we were turning on noise, because there you are in particular limited to certain types of noise amplitudes, and in particular if you went too high with the noise amplitude, you would also violate the Markovian weak coupling condition, and therefore there we simply put a cut on it. And that's the incarnation where this type of problem really plays a practical role. In unitary control, if you have coupled systems, they are somehow self-regularizing, and these delta pulses usually do not occur.
What about analog systems like simulated systems? In that case, because it's hard to turn off terms there, you don't really have like controls, right? You have more...
Sure, this is of course a question to which extent the experimental system really follows your theoretical model, and whether all the interactions which are pertinent and present in the system are really encapsulated in the model. In these situations, it usually pays to somehow start with a simplified model and simply go for the optimal controls under those, then try to understand what this type of pulse sequence does. And since ultimately you are anyway relying on numerical models, you simply allow these terms to occur and see what optimal control does with them, and to which extent the idealized or the controls optimized under idealized conditions then will have to be tweaked in order to cope with the realistic system. And that's something which one can often do. Along similar lines, there's one recommendation, and that is very often in experimental groups, they pay an enormous lot of money for the very quantum bit of what they want to have a look at. For instance, their ion trap, their diamond, you name it. That's where they put the big money. Usually they have very little money for the control unit because they think, that's trivial anyway, it's semi-classical, and I'm going to pay my money on the quantum side. In these situations, it's extremely helpful to really have a look into numerical optimal control and simply see to which extent, for instance, the limitations in the precision of your control prevent you from really exploiting all the quantum goodies your quantum system could offer you. And then simply put these results into the grant proposal and simply make a strong case that not only do you have to spend the money on the quantum side, but also on the arbitrary waveform generator and the electronics that go with it. And this is something which people very, very rarely do. And where I think that also on the proposal side, there would be a very good interplay between theory, input, and practical appreciation. And that's exactly where these non-idealities also come into play. And very often, if you can't get the most of out of your experimental system, it may not be the dirt effects on the quantum side. It may be that the dominant part that prevents you from getting what you should is on the control and electronics part.
But even like that, when you consider different noise models, you always consider that they are independent from each other. Yeah, you don't consider that they might play together to make things even worse.
Yeah, you can also have correlated noise, and as soon as you can simulate it, you can also plug it into your optimal control. And I think that's really the good thing. Let me simply stress that I advocate for a closer collaboration between the theory and the experimental part, because you could really develop that in stages, and it really pays and deepens your understanding of the system. And you see, of course, one can think about correlated noise, which is also very difficult to model, but it could very well be that you have overlooked a simpler source of non-ideality, and now you are trying to fight it with models of correlated noise, and therefore having really a good hierarchy of how to make things more and more realistic and also make your model more and more complicated is what is required.
So thank you for the talk. It's not much of a technical question, maybe rather a philosophical one. So do these symmetry conditions you showed that make a system controllable, do they apply on larger systems or maybe the universe as a whole? In other words,
to larger systems, you say?
Yeah.
Yeah, in principle, these principles are universal. They are not limited on system size. It's what the system size does, however, limit is, of course, the feasibility and ease with which you can numerically come by. But just as I said before, you see, if you start out with smaller systems whose symmetries you really understand, and then you enlarge it, usually if you don't change the model, the symmetries just, so to say, grow with the system size, and you have understood the principles, and then it simply scales. And of course, there may be instances where enlarging a system and changing its nature then also, of course, changes the symmetries. But if you want to have a very general answer here, let me simply say that what is, so to say, now emerging gradually, and what we are trying to prove is that we have these types of system algebras which follow these type of branching diagrams that we got with the help of Robert, and that in principle all the members in the branch, even if you go down, are somehow symmetry characterized, and they are symmetry characterized in a unique way. And therefore what we would hope to arrive at is really a full dual picture of the system algebras on the one hand side and their symmetries on the other, really in the sense of a quantum Noether-type of theorem, so that we have a von Neumann type of duality between the symmetries and the system algebras. And that is, so to say, the wish we are pursuing, but it seems the way till there is not always trivial. But that's also what you will hear us trying to discuss when we are on the corridors here, the three of us. Yeah?
Is there anything that this theory can say about the effect of sort of control and precision? As in, if you control it slightly differently, do you end up in a nearby state, or do you end up somewhere completely different in your Hilbert space?
Yeah, sure. The groups might be slightly different if you add further interactions. So if there's something where, so to say, the system obeys a certain symmetry, and now you simply turn the amplitudes slightly higher such that this type of symmetry is violated by maybe nonlinear effects, that's exactly something which you should be able to see.
And is there a way to tell where you'd get sort of something where you'd be more mixing, or where you'd end up sort of close controls end up to close states, or?
Yeah, let me simply say, if you are pursuing different types of methods, as I advocated here, then this might also help you to judge certain precision. So for instance, if you simply follow the nuts and bolts approach, you model your system, you plug it into the computer, let the algorithms run, administer an optimized waveform to your system, and get a certain type of figure of merit, sometimes you don't know whether this is really a global optimum, whether it's close to a global optimum or not. If you can model the system and really instead of, so to say, having an optimal control type of algorithm that simply drives your system with the experimentally controllable degrees of freedom, as control amplitudes, to a certain type of precision, if instead of such an approach, you can also back that with a more global analysis as a flow on the group, you can compare these two different types of precisions, and maybe the mathematical one with a flow on the group tells you that you should be able to really reach your target with unit precision. And then if you simply administer that to numerical optimal control and you get somewhere close to error correction threshold errors, then you are happy. If the algorithm drives you significant below, then you know that there is a gap which your model doesn't really explain. And therefore, in particular, when it comes to error analysis, going both ways and really taking a dual rail approach really does pay. And very often, of course, in closed systems, if this question is well posed, you know that you should be able to get unit precision, and therefore whatever falls short of 100% is something like an experimental error, or you didn't allow for enough time, or you didn't really model relaxation, although it's weak but still present, you simply neglected that. That would be some of the sources of error. And then you simply let it run via symmetry analysis, and if this really tells you there's no symmetry rule that should forbid you from really getting full precision, that's what should trigger a discussion. Yeah? And therefore, really, control theory as an upshot really is at the interface between theory and experiment, and it's really good to go from one leg to the other. And to have a numerical trail and a theoretical algebraic trail and really discuss the two of them, the interplay, and of course, at times also the divergence. Yeah, Said?
Thanks for your lectures. I have a question. And also, pardon my question because probably it's a very ignorant question. So if, for the case of non-Markovian and Markovian, and then for the state transfer, there's not much different. I mean, probably not different between the open loop and closed loop. My question is, what happens if we consider, let's say, unitary synthesis for the just simple gate? Let's say, do you think the closed loop or the open loop will, will give also the same result like the state transfer case for both non-Markovian and Markovian, or how? I mean,
yeah, that's an interesting question, and maybe I should make all of you aware of the fact that there are early papers by Lorenzo Viola and Seth Lloyd,
yes,
who long ago, I think in 2000 or 2001, discussed that for really having a universal quantum simulator in terms of quantum maps,
okay,
you would not only have to have all the Markovian processes included, but also closed-loop feedback, which then simply makes use of memory terms. Okay. And I simply want to underline what I said before, that when it comes to quantum map simulators, there really is a difference between Markovian and non-Markovian ones. So really, there are cross maps, let me simply stress that once again, which are not solutions of a Lindblad master equation, and all the Markovian ones have to be solutions of a Lindblad master equation. So there is a one-to-one correspondence, and therefore, when it comes to quantum maps, closed loop will be more powerful than just open loop. In state transfer, there's also one subtlety which I did not emphasize, but which was on the slides, and that is that these reachable sets and the transitivity only was obtained in the closure. So that means that, as it may happen in open quantum systems, you wait for an exponential decay, and that can take you a long time. And it's exactly this type of long time which goes into the closure. And the interesting thing, and I don't know of any example to underline it, but it would be very interesting to find one, would be to have an example where you have a target state, which is in the closure of the reachable set of a certain initial state under Markovian conditions. So it's really sits in the hull. And once you have closed loop feedback, it drops from the hull into the interior of the reachable set. And that is, of course, something which can happen. And it would be mathematically very interesting to see something like this. And may also be, if it happens in a class which is experimentally pertinent, then this would be, so to say, a good quantitative caveat in order not to oversell these theorems. And I'm quite aware of that. So under non-Markovianity, something from the closure may fall into the interior. That's natural. And maybe one could arrive at a very nice example. I haven't thought about an example, but if you can come up with one, you'd be most welcome.
Thanks. Thanks.